Welcome back to the Cave of Science, and today we're going to do a few electron configurations. If you recall, using the Hund's rule, and you can look this up, there's plenty of tables and pictures out there and so forth. We go 1s2, 2s2, 2p6, 3s, 3p6, 4s2, and 3d10, and then it goes onward from there. And remember, you always fill up these suborbitals first. And if you have less, let's say the 6, you only had 5, you'd put 1, 2, 3, 4, 5, 6. And we're going to go through some of these and take a look at them. If you were to write it out, here's how it would look written out. So let's look at oxygen, and it has an atomic number of 8. So we're going to do these long form. So 1s, I'm just going to start by putting some of these down. And then 2p has 3 suborbitals. So oxygen, we got 8 electrons. So we can go 1, and we fill this up. 2, notice up spin, down spin. 1, 2, 3, 4, 5, 6, 7. Notice I put parallel spins in the suborbital here. I got 1, 2, 3, 4, 5, 6, 7, and then 8. So that's what oxygen would look like. Let's take a look at chromium. Chromium has 24 electrons. So I'm going to write this out again. 1s, 2s, 2p. Then we have 3s, 3p, 4s. I don't know exactly where this is going to take me, but we'll find out. And then there's 5 there for 10 electrons. Okay, so we got 24 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and we're going to come back. If you remember, chromium is one of those oddballs. 19, 20, 21, 22, 23, 24. Well, you may ask, well, why didn't you put 2 in the 4s? If you recall from a previous video, a half full subshell with 3D has greater stability. Chromium and copper are the 2 oddballs. Otherwise, we would fill the 4s. Well, let's do one where we would fill the 4s. So this one definitely is one of the oddballs. Let's take, we can take calcium. So calcium, atomic number of 20. And let me push that up a little bit. So we got 1s, 2s. And the more you do these, you're going to find out they're going to go pretty quick. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 3s, 11, 12, 3p, 13, 14, 15, 16, 17, 18, and here's the 4s, 19, 20. So there's calcium's configuration. And if you were to write that out, you'd write 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. You can work backwards on these also if you were given this configuration or this numerical way of writing it. Or if you were given this, you would just add these up. These are the electrons. And remember, for everything on the periodic table, they're electrically neutral. So the number of electrons is going to equal the number of protons, which is your atomic number. Now, if you happen to run into a charge, let's say it was like, oh, calcium plus 2, then it would lose these 2 electrons here. If we had calcium plus 2, these 2 would be gone. Likewise, if you have an anion, it gains an electron. So if you happen to see that. One other thing you're going to run into every once in a while is the kernel. And the kernels are going to be neon, argon, and krypton. You can get into xenon, but these are the 3 you run into. Remember, these are the inert gases, and they don't combine with anything because they have a full outer subshell. Remember, when you're looking at electron configuration worksheets, you're really, especially when you use the kernels, you want to use just the valence electrons. And I'm going to work with neon on here. So neon has an atomic number of 10. So neon has an atomic number of 10. So 1s, 2s, 2p. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that is this is a very stable configuration because it has a full outer shell, and it also fulfills the octet rule. So it's stable, full outer shell. And it fulfills octet rule. Now, what you're going to see sometimes, oops, move that over a little bit for you. What you're going to see sometimes is you're going to see the neon kernel. And as I mentioned, typically when you see the kernels, it's going to be a neon, argon, or krypton. And I'm just going to do one with neon. So let's do one of these. So if neon is going to be our kernel, it's typically going to be these in this row, or in this period, so to speak. If argon's our kernel, then it's going to be these all the way up to bromine. And if krypton, then you would start working here and so forth. So for neon, we can use the neon kernel for sodium, magnesium, aluminum. And so right now, I'm going to pick aluminum, and I'm going to write it both ways for you. So aluminum, atomic number 13. So aluminum with atomic number 13. So we have 1s, 2s, 2p, 3s, and then if you remember, after the 3s, we have the 3p. And we have 13 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So if we look at aluminum, that is going to be our electron configuration. Now, we could also write it, so we could call it 1s2, 2s2, 2p6, 3s2, 3p1, 4, 10, 12, so we have 13 electrons there. Now, let's write it using the neon kernel. So if you remember, right, if you remember up here, so neon's the first 10. So there's our first 10 right here. So the shorthand way of writing this, the kernel is always in parentheses. So neon, and that's telling you these are being used here then you would write it 3s2, 3p1. So you don't do the lower levels at all. You're just looking for aluminum's valence electrons, which would be these. And that holds true for other elements on periodic too. So don't get confused by the kernels. They just bring you the interior electrons, and then you can go ahead and put in your valence electrons. Alrighty, let's see, anything else on this? I think we can do maybe another one. Now let's try bromine ones. Bromine has 35. And we can use, for bromine, we can use the argon kernel. So Br is 35. And we can go ahead and use the argon kernel. So we could say the kernel of argon. And remember, if you remember the periodic table, we look at argon as 18. So we would need to show another 17 electrons, because there's our kernel. So if we look at bromine, there's our kernel. That has 18. Argon has an atomic number of 18. So 35 minus 18, we'd have 17 electrons left to show. So we would end up being in the 4s2, 3d10, 4p5. And if you wonder where I got these values from, after 3d10, we go to the 4p. Oops, I should put that up there. And that would give us another 6 there. And again, really, they all work the same way if you follow Hund's rule on there. So this would be the shorthand way. Argon is 18, so we have to show 17 more. 35 minus 18 is 17. There's our 2, 10, there's 12, 5 more would be there. The longhand way would be all the previous subshells filled there. There's plenty of problems you can do. You can make up your own. So I hope this helps, and we will see you again on the next one.